This part explains why category theory begins by refusing the usual question about what a thing is. A category answers the question of what this thing is by refusing it. An object is fixed only by its morphisms, the arrows into and out of it, never by any internal stuff. Eilenberg and MacLane coined categories as mere scaffolding for functors. The chapter inverts that accident into doctrine. Category theory is formal ontology, the science of a domain's relational skeleton. What survives is what a structure does, determined up to isomorphism by its web of maps. The whole arc is this reversal, from objects with interiors to objects as positions, and why physics, mathematics, and philosophy converge once relations, rather than substances, are taken as primitive. This section explains why category theory took hold across physics, mathematics, and philosophy. The reason is that it works as a formal ontology of relations. It fixes what a thing is by how it maps to everything else, never by internal constitution. An object carries no intrinsic content. Its identity is exhausted by the morphisms into and out of it, its position in a web rather than any substance of its own. Eilenberg and MacLane thought they had coined only a convenient language. The surprise that does the real work is that this language is a metaphysics. It detects the same structure across algebra, topology, and quantum mechanics precisely because it discards everything except how the parts hang together. Relation is primitive, object derivative. That is the move you can now replay for any domain it touches. This section explains why category theory carries philosophical weight. Category theory earns that weight as a counterexample engine. Every monospecies of the form, everything is X, everything is a set, Cowan's quantificational criterion of being, meets a topos where it fails. In one topos, the quantifiers do not interpret. In a Zariski topos, you can prove that there exists an X, such that not f of x, while the planar claim that there exists an x, such that not f of x, while the planar claim that there exists an x such that f of x stays underivable. So the questions shift from answers to structure. Mathematics is a network of mutually irreducible universes, and category theory is the instrument that reads the relations across them. Kroll's inversion carries the surprise. Category theory is the most Platonic mathematics. It treats totalities as already existing, seen from outside, non-constructively, even as its own internal logic stays intuitionistic. Platonism here becomes a method rather than a doctrine. The counterexamples refute foundations without replacing them. This section explains why category theory carries philosophical weight in Kroll's chapter, and what kind of act that weight consists in. A framework earns philosophical weight by refuting rather than by founding. Kroll's chapter is one sustained demonstration that category theory's payload in philosophy is a counterexample machine rather than a new bedrock. Every grand universality claim meets a constructed exception. The claims are these: that every object is category theory. Describable, that category theory is a new language for all of mathematics that existence reduces to Quine's quantifier. Against each of them stands an alter theory with no model in the original. One such exception is a Zariski topos, where there exists a Zariski topos, where there exists an x such that the double negation of f of x holds, yet there exists no x such that f of x itself holds. Hence his scattered question marks. The meta-theorems are locally true and globally false. Category, theory, and set theory are non-conservative interpretations. Each one reshapes what it describes rather than translating it neutrally. The generative primitive is this: a theory's sharpest philosophical act can be purely negative. This section explains why category theory fails to explain physical phenomena, and why Wohotoichi treats that failure as his instrument rather than a defeat. His thesis inverts the expected question. Category theory does not explain physical phenomena, and that very failure is what he puts to work. Start with what a working mathematical explanation does. It binds an abstract structure to a concrete situation, the Königsberg bridges, the hexagons of the honeycomb. It keeps direct contact with the case, and it carries at least a minimal predictive input. Topological explanation is the sharpest instance of this, and it serves as the contrast class against which category theory is measured. Category theory abstracts one level higher. It analyzes theories, concepts, and models. It is a theory of theories, so it never touches the heat in a rod. The generative move is that the thing to be explained is fixed by what category theory lacks. The question then becomes why an abstraction too high to explain anything can still deepen understanding. Probing that takes the measure of the notion of explanation itself. Its reach goes past the narrower question of where category theory sits within physics. This section explains how Wohltowitz relocates a familiar denial about category theory rather than simply accepting it. The chapter turns a flat no into a change of address. Ask whether category theory explains physical phenomena, the way a graph theorem explains the Königsberg bridges, where the phenomenon is inherited directly from an abstract property of the system. On that measure, the answer is no. Category theory never reaches down to the concrete. It offers no prediction, so by the standard account, it offers no prediction, so by the standard account, it explains nothing. But the thing to be explained has simply moved up a level. What category theory explains is the theories of the world, not the world itself. It explains, for example, why standard quantum mechanics resists a realist reading, because that theory lives in the topos sets, which is the setting of topos quantum theory. The properties category theory accounts for are meta-abstract. They are features of our conceptual systems rather than features of phenomena. This section explains why making and knowing are the same process, run with its arrow reversed. Both a poietic act, bringing an artifact into being, and an epistemic act, acquiring knowledge, actualize the same static triple, a prescription or hypothesis called OP, a perception called PO, and quality criteria called QC that relate the two. The sole difference is the direction of fit. Poiesis evaluates the world, PO against the word OP. This is words into flesh. Episteme runs it the other way, evaluating the word, OPE, against the world, POE. These are Searle's two directions of fit, one skeleton beneath them both. This is what the chapter is for in the volume. It stages category theory as the apparatus that asks whether successive versions OP1 becomes OP2, and so on, still describe the same object with identity preserved under structure, mapping morphisms. This section explains how knowing and making are a single process run in opposite directions. Knowing and making are one process run backwards. Poiesis turns word into flesh. A prescription becomes an artifact. Episteme turns flesh into word. An object becomes knowledge. Lubach factors both the same way. An invariant pattern is actualized into a succession of states by animation, the human intervention that is the nexus of the static and the dynamic. Each process is then a triad of descriptions: the object as prescribed, the object as perceived, and the criteria binding the two. The process evolves by transforming those descriptions. Category theory enters only to name the arrows. A process is what its relations do, monitored through the morphisms between descriptions rather than through the essences of things. This section explains why category theory conceals an asymmetry, one that may echo the direction of time. Reverse every arrow, and category theory is unchanged. Product and coproduct are the same statement, read in two directions. Yet the moment objects become sets carrying structure, that mirror shatters. Across the categories set, top, group, rings, and Banach spaces, the product is always the Cartesian product, while the coproduct fractures into 6 unrelated species: disjoint union, free product, direct sum, and tensor product. Semadeni's diagnostic invariant is the forgetful functor to set, which preserves products but never coproducts. The many-to-one shape of a function, f from x to y, is the seam. Behind it causes precede effects, the thermodynamic arrow leaking into mathematical thought. The chapter's telos in the book is a concrete site where physical time asymmetry surfaces as literal categorical structure rather than metaphor. This section explains why a perfect symmetry in category theory breaks the moment you build real mathematics from sets. Category theory is perfectly self-dual. Reverse every arrow and every theorem maps to an equally valid one, yet the concrete categories built from sets with structure betray this symmetry. Their products are the Cartesian product almost everywhere, while their coproducts fracture into 6 unrelated constructions: disjoint union, free product, direct sum, tensor product. Semadeni's move is to read that broken symmetry as a fingerprint. The forgetful functor to set preserves products but not coproducts. The asymmetry traces to the many-to-one direction baked into the very notion of a function of from x to y, which in turn echoes causes precede effects, the arrow of time. The formal apparatus is time symmetric. The mathematics we actually build is not. This section explains how Liszt recasts levels of reality as a category, and why supervenience by itself does not force one level to reduce to another. Supervenience is a map, a relation between levels rather than a substance, and that relational reading is the whole move. A level of reality is defined only by which other levels it lies over, and by how the finer levels it lies over, and by how the finer level determines the coarser. Liszt packages this first as a pre-ordered class, then as a posital category, where each supervenience relation is a unique surjective function. Once levels are the objects and supervenience is the arrow, every metaphysical question becomes a question about which morphisms exist. Whether the mental reduces to the physical, whether grain is emergent, all of it turns on which ROs are present. Whether the mental reduces to the physical, whether grain on which arrows are present. Dewey, Fletcher, and Hudetz inherit this frame in order to repair it. They patch the places where Liszt's inverse limit construction fails, and they pin down exactly when supervenience forces reduction. The surprise is that supervenience alone does not. This section explains what a level becomes once category theory takes hold of it. A level is a position in an order. Reality strata become objects, and supervenience, higher fixed by lower, becomes the single arrow relating them. Dewar, Fletcher, and Hudetz take Liszt's insight that these arrows compose, meaning identity on each level, and transitivity on each level, and transitivity of supervenience, and read the whole as a concrete posital category, sets of possible worlds, surjective maps between them. Once levels are objects, and supervenience is a morphism, metaphysical questions turn structural. Two-level systems are the same when they are isomorphic, and reduction becomes a factoring condition on maps. The chapter is the book's proof that category theory bites on metaphysics and not only on physics. This section explains why the smooth structure of four-dimensional spacetime is forced to be exotic, starting from the lattice of quantum mechanical projections. Non-distributivity is the whole engine. A quantum system's projections form an orthomodular lattice, call it L, that no single Boolean subalgebra covers, unless L were already classical. Each Boolean subframe, what Bohr called the classical glasses, spins up its own Boolean-valued model of ZFC, and hence its own object of reals. Parametrizing spacetime by these local frames is exactly assembling a chart atlas. The obstruction transfers intact. No global Boolean frame becomes no single chart cover. Since standard R4 is the unique smoothing that admits a one-chart atlas, the spacetime 4 manifold is forced to be exotic. What the chapter isolates categorically is the residue. The colimit is the principle gluing local Boolean subobjects into one structure, precisely where the gluing failure lives. This section explains the colimit as a structural primitive, drawn from the work of Bielas and Kroll. The colimit is the whole thing, the smallest structure into which all the local pieces glue, that is the primitive Bielas and Kroll handju. No single Boolean algebra covers the quantum lattice of projections. L. Cochin and Specker forbid a global truth, valuation, exactly as no single chart covers the space-time manifold. So you stop looking for one covering piece. Instead, you assemble the many classical reference frames into their colimit. Here is the surprise the chapter is for. This same categorical gluing, applied to Boolean-valued universes of ZFC, each carrying its own reals, forces M, homeomorphic to R4, to be exotic smooth. The failure of a one-chart atlas and the non-distributivity of L are one. Obstruction, read twice. This section explains why a singularity is an obstruction only relative to what can probe it. In standard general relativity, the differential structure dies at the boundary of the manifold, so no curve can cross it. The wall is real because the tools stop, not because space itself ends there. Helle and Kroll make one move, change the logic to intuitionistic, and the real line grows infinitesimals. Every point acquires an interior, a monad, its own fiber of degrees of freedom. Differentiation becomes purely algebraic, every function smooth to any order, so the obstruction never arises. You do not cross the boundary along a curve. You descend into the point and read what was always inside it. The seed this chapter plants for the whole book is this: geometry's limits live in its logic, not in its space. This section explains why the singular boundary of space-time behaves like the edge of a chosen mathematics rather than a wall inside the world. The singular boundary, the boundary of M, is where a chosen category runs out. Read it as the limit of the tools you brought, not a barrier standing inside the space itself. General relativity completes space-time to M bar, which is M together with its boundary. Its smooth tools die at that boundary. Nothing crosses. Helle and Kroll leave the geometry untouched and change the ambient logic. They embed M in a topos whose intuitionistic internal logic admits infinitesimals. This move is synthetic differential geometry. Each point now holds interior structure, a monad graded by a differentiability degree, k. The Big Bang singularity is simply k equals 0, a point with no infinitesimal neighbors. Crossing the boundary becomes a contraction from m infinity down through m sub k and onward down to m sub 0 with k readable as quantist time. Enlarge the category and the boundary turns interior. This part explains why the renormalizability of quantum gravity is a fact about logic rather than about gravity. Renormalizability belongs to the logic you quantize gravity in, rather than to gravity itself. The Feynman diagrams of four-dimensional quantum gravity diverge because interactions sit at a sharp point on a smooth manifold. That sharpness is an artifact of classical logic, of the excluded middle forcing every real number to be either zero or invertible. Drop the excluded middle. Inside a topos, the real line grows nilpotent infinitesimals, quantities where d to the power k is zero, while d itself is non-zero. Each space-time point then acquires a monad, an infinitesimal cloud where gravitons interact rather than meeting at a single geometric point. With the interaction spread across that cloud, the ultraviolet divergence has nowhere to form. Pure perturbative quantum gravity becomes finite, and certain supersymmetric versions with matter become finite too. It is the same move as choosing a topos so that an impossible object can exist. This section explains how quantum gravity's divergences can be cured by changing the logic beneath space-time rather than the fields. The cure operates one level down on the logic that the space-time lives on, while the fields themselves are left untouched. Drop the law of the excluded middle and work inside a topos instead of the category, SET. Once you do, the real line stops being made of points. It sprouts nilpotent infinitesimals, numbers d for which d to the k equals 0, while d itself is not 0. Each space-time point then carries a monad, an infinitesimal halo surrounding it. Let gravity propagate on those monads, and the perturbative Feynman diagrams that were incurably divergent on the smooth manifold M4 come back finite. The infinitesimal structure absorbs what the point-like geometry could not. The generative primitive is this. A physical theory inherits exactly the objects that its ambient topo's internal logic admits. Refuse a single logical law, and the geometry, along with its divergences, reorganizes itself around the refusal. This section explains how one categorical construction turns static concept analysis into the analysis of complex systems and time series. A concept is the fixed point of an adjunction. Will, Hardegree, and Birkhoff all name the same object, the Galois connection between items and their properties whose closed pairs form a lattice. That lattice is static, one system at one level. The chapter's move is to stop editing the lattice and instead to index it. You build a functor from a semilattice into the category of complete lattices. The elegance is that hierarchy and time are the same index. A semilattice of levels, or a chain of successive stages, feeds one identical construction. Evolution needs no new machinery. The static invariant diagrammed over a base category already is the dynamics. Change what you index over, and time series analysis falls out of concept analysis, unchanged. This section explains what a concept is and how to make concept analysis unfold in time. A concept is a fixed point of an adjunction. The Galois connection between items and properties closes each set, and the pairs it stabilizes, extent against intent, assemble into a concept lattice. That is the entire static theory. Will, Hardegree, and Birkhoff coincide exactly here. The chapter's move is a single primitive. To make concept analysis temporal, do not rebuild it, index it. replace the one lattice by a functor from a semilattice into complete lattices. Each level of complexity, or each moment, is an object, and the bonds are its arrows. A time series is the degenerate index, a chain. A hierarchy is a branching semilattice. The generative residue is this. A dynamics is a functor out of a shape category, and the shape alone separates evolution from stratification.